Okay, so until as recently as 2010, the vast majority of pictures, motion pictures that were being shot on film. And by that time, professional still photographers had largely embraced digital cameras. But it was only just a few years later when that situation completely reversed and film was becoming a rarity. So what led to that very rapid digital takeover? So it required several pieces to fall into place. Firstly, the cameras, most importantly, the recording and the workflow technology, and of course the cost had to be right. So to understand the camera piece of the puzzle, we need to start actually by looking at the characteristics of film and how that compares to digital. And I'll talk about some of the early digital cameras before looking at the recording technology itself, which in the beginning was videotape based, before transitioning to hard disks and then to solid state eventually. And finally, we'll have a look at some real recorders. Now, inevitably, my company is going to feature quite a lot in the story, for which I apologise, but I should make it clear that everything I'm saying today is actually my own personal viewpoint. Okay, so colour motion picture film. Film consists of an acetate base, and it has multiple layers of emulsion laid on top of it, which are sensitive to either red, green, or blue light. And to capture an image, each frame of the film is briefly exposed to light by opening a shutter. Now, the ratio between the darkest and the brightest details that you can capture on film is called dynamic range or latitude, and it's measured in stops, at least it is in movie land. Typical negative film is around 13 stops, which, if you think about that in digital terms, corresponds to 13 bits. This is actually quite a high dynamic range, and it makes film a very forgiving medium for shooting with, and it can tolerate a reasonable amount of either over or under exposure without losing important details. But what's the equivalent resolution of 35mm film? Now that's a much more difficult question to answer. The light-sensitive elements on film are silver halide particles, and they're generally around 1 micron across. And when the film is developed, what happens is much larger dye clouds form around those exposed silver particles. And the dye clouds are the fundamental image-forming elements, if you like, on film. But they vary in size quite a lot. And there are also several overlapping layers of them in different layers of emulsion on film. And to further complicate things, film has got grain. It's caused by the clumping together of the dye clouds in those layers of emulsion. And that has the effect of reducing the perceived sharpness of images taken on film. So taking all of those factors into account, a reasonable estimate for resolution might be about, say, 5,000 pixels across. Now, in a digital camera, the light-sensitive component is called a sensor. And that usually consists of a rectangular array of pixels. The most common type of sensor that's used today is based on CMOS technology. And the way that works is in each pixel, incoming photons are converted to electrons, which are then stored in a well. At the end of the exposure time, the charge in the well is transferred out and the voltage is converted to a number which is proportional to the amount of light that is seen. Now, the dynamic range of the pixel is determined at the upper end by the number of electrons that can be stored, and at the lower end by noise. Okay, apologies for the sound problems, folks. I trust people can hear everything I'm saying. Okay, so just to recap, the dynamic range of a pixel then is determined at its upper end by the number of electrons that can be stored, and at the lower end of the dynamic range it's dominated by noise. Now, there are very many types of noise in a digital sensor, most of which can be reduced by using careful design. But one thing that can't be reduced is shot noise, and that arises because of the discrete particle nature of light itself. So a constant light source will emit photons essentially at random, which means that the number emitted in any given time period will vary slightly. As more photons are collected, the percentage difference between them becomes less significant. So if you want to reduce the effect of shot noise, either exposure time or the pixel size must be increased. So it follows that for a high quality image sensor, it must be as large as possible. But practical considerations obviously impose an upper limit. Larger sensors are much more complicated and expensive to manufacture. And of course, the larger sensor needs a larger lens, which is heavy and results in a very heavy and bulky camera. So camera phones, I'm sure everyone has one on them at the moment. Generally, these can capture 48 megapixels or even higher, whereas most of the cameras that are currently being used out on film sets for your latest Hollywood blockbuster are probably no more than 8 megapixels. So why aren't all film crews just using their mobile phones? Why are they bothering with all these expensive cameras? So it comes down to what I was just saying about the relationship between pixel size and image quality. The camera phone sensor pixels generally be around a micron, compared to perhaps 10 microns, and that's square as well, for a digital cinema camera. So obviously you can see that leads to a vast difference in the ability of those pixels to collect light and in the dynamic range. And dynamic range generally is a much more important factor than resolution for a high quality image. So consider also the resolving power of the actual optical system in a camera phone is nowhere near as high as the sensor. So these things generally have cheap plastic lenses, and they will not be able to resolve the detail that the sensor can. In fact, they act as a kind of a low pass filter on the sensor, which actually helps to avoid aliasing problems. But really, the very high pixel counts that you have in camera phones are pointless, is really the lesson. And modern phones actually only achieve sort of the apparently impressive results that they do by having very clever noise reduction and post-processing techniques built in, sometimes now even using AI techniques to reduce visible noise. But if you look at these images on a big screen or to get them to close scrutiny, it really doesn't stand up. So maybe that's something to bear in mind if anyone's looking for a new phone, and don't always go for the one that has the highest resolution. It doesn't mean you're getting the highest quality. So colour. CMOS sensors essentially respond to all wavelengths of light, including some of the non-visible ones, and that results in a monochrome image. So two main techniques are used to capture a colour image. The first one is on the left there, you have a beam splitting prism, and that splits the incoming light into the red, green, and blue components, and each of those is captured by a separate sensor. And that technique is traditionally the one that's used by television cameras. And the second technique on the right is called Bayer pattern. And what that involves is putting either a red, a green, or a blue filter over each pixel. The most common way of arranging those there is called the Bayer pattern, where each quad of pixels has 2 greens, 1 red, and 1 blue. Well, that makes sense, having more green, because human vision is the most sensitive to green light. To form a full colour image from the Bayer sensor, it's necessary to interpolate those missing colours at each photo site on the sensor. And there are many algorithms that have been devised to do that, but they all have various drawbacks. They're all defeated by certain images and so on. But despite that major drawback, the simplicity and the generally lower cost of the single sensor approach outweighs the downsides, and all modern digital cinema cameras are single sensors. So again, motion picture film cameras generally use a rotating mechanical shutter, and that alternately allows light to reach the film, and then it blocks it part of the frame. So the film is advanced only while the shutter is closed and blocking light, and the speed at which that shutter rotates determines the frame rate, and the exposure time is controlled by the frame rate and also the relative time during each frame period that the shutter is either allowing or blocking light. And that's known as the shutter angle. And that's altered by adjusting the shape of that shutter, which generally has 2 movable sections that can be adjusted. And you can see the diagram there just shows you how different shutter angles affect the relative exposure time per frame. So most digital cameras don't use mechanical shutters, although there are a few that do. For electronic shutters then, there are 2 main types. There's a global shutter, where start and end exposure time is the same for all pixels on the sensor, and exposure is then followed by a separate readout period whilst the sensor is not integrating light. On the other hand, you also have a rolling shutter where exposure for each sensor line is, if you like, staggered, so that only a narrow band of lines on the sensor is being exposed at any one time, and that band moves generally from the top to the bottom of the sensor. And then readout of previously exposed lines occurs in parallel whilst other lines are being exposed. So because on a global shutter, the exposure and readout have to be serialized, that causes a compromise. Usually either the dynamic range or maximum frame rate is reduced. And that means, again, that rolling shutters are actually the most common, despite the fact that they cause some very interesting image artifacts. So you may have seen some of these. On the left there, you can see what should be vertical lines, or at least I would hope so, unless the maintenance folk at Alexandra Palace have been neglecting their duties. That should be vertical, but because it was taken from a moving train, you can see, because of the rolling shutter, that's actually caused those lines to slope. And you can get even more dramatic effects with very rapidly rotating objects, like, for instance, the aircraft propeller on the right, which is completely distorted beyond all recognition. And the other effect you can get is a strobe light or any flash of light can appear to only illuminate just part of an image rather than the whole image. So now let's say looked at some of the basic differences. Let's look at some of the actual cameras that were on the market in the early days. So this is the Thomson Viper film stream camera, introduced in 2002. Thomson were a very well-known manufacturer at the time. They television cameras and other equipment. And the Viper was a derivative camera derived from television cameras, but specifically tuned for the needs of filmmakers. It was a 3-sensor design with a prism, and it could output a full 1920 by 1080 resolution RGB image. That resolution, by the way, is called HD, which you've probably heard. And it did that without any of the in-camera processing that most television cameras at the time would have done. And that enabled you to get a higher dynamic range out of that camera and more freedom to manipulate the pictures after the fact. Now, the interface from the camera was a broadcast standard high definition serial digital interface, or HDSDI for short. And it used 2 of those links in parallel to handle the RGB image. You may know that television images generally are not RGB, they are in luminance and 2 chrominance channels, which again is a kind of a compression technique. So the RGB image would be captured uncompressed, typically onto a hard disk-based recorder. Some of the notable films that were shot using that camera were Michael Mann's Collateral and David Fincher's Zodiac. Now, Sony, I'm sure you all know Sony, they're a very large manufacturer, and they're not only consumer equipment, but also broadcast segment as well. So over the years, Sony have created a whole load of cameras that were targeted at digital cinema under their Cine Alta brand. And that started with the F900s Camera in 2000. And that was used to shoot Star Wars Episode 2, Attack of the Clones. There may be differing opinions over the quality of that film from the audience, but it did have the distinction of being arguably the first major motion picture that was shot 100% digitally. Other notable models that Sony produced were the F23, which was another 3-sensor camera like the F900, and the F35, which was the first single-sensor camera that they produced. Now, all of those were HD resolutions, so 1920 by 1080, and they were capable of relatively limited frame rates, so generally no more than 30 at full quality, 60 at the reduced quality mode. And again, you could record the output of all these cameras via their HDSDI interfaces, uncompressed onto hard disk recorders. But Sony also promoted very heavily capture onto their own tape formats, which were HDCam and HDCam SR. And those tape formats used a very mild compression to reduce the rate down. Now, Dalsa is a Canadian company, which you may not have heard of, and they're primarily known for designing high-quality image sensors. So their image sensors go into military and satellites, that kind of thing. They decided to get into the cinema camera market in 2003, and the Origin camera they showed for the first time at the National Association of Broadcasters NAB show in 2003, and that's where I first saw it. And I realised that the hard disk recording technology that I was working on at the time could quite easily be adapted to work with this camera. And my company subsequently went on then to produce the recording solution for it. In some ways, it was well ahead of its time. It had a 4K resolution, so 4,000 pixels across, that's 16 bits per pixel. And it outputted that raw Bayer data as opposed to sort of processed data, as the other cameras were doing. So it had a higher resolution and also a higher dynamic range. It also had a rotating mechanical shutter and an optical viewfinder, just like a real film camera would have. The interface to it was via a fibre optical cable, rather than the fragile video coaxial cables that a lot of the other cameras used at the time. But despite all that, it was not a commercial success, unfortunately. And in fact, also withdrew altogether from the cinema market in 2008. The reasons why it failed are many and varied. There were technical image quality issues with the sensor, unfortunately, which they never managed to quite solve. And of course, the camera, you can probably see by looking at it, the camera was very large and heavy. Another factor at the time was the very high cost of actually storing and processing that 4K data. So that's approximately 4 times the data rate, or a bit less because it was raw, but at least 2 to 3 times more data than HD. And at the time, that had quite a high cost implication. So despite many, many tests, the camera was never actually used as a main camera on a major picture. But that's not to say that it didn't have any interesting uses. The high resolution actually was just what the producers of the James Bond film Quantum of Solace were looking for when they wanted to deliver a fairly complicated visual effects shot where Bond, you can see that played by Daniel Craig, and Camille, who's played by Olga Kurylenko, they jump out of a plane without a parachute and they go into a sinkhole in the Bolivian desert. So it was that I found myself in, I think it was February 2008, in a freezing cold wind tunnel near Bedford, with no less than 8 of these massive Origin cameras, plus their recorders, and another 7 HD video cameras, which had been arranged 360 degrees all around this wind tunnel, just like a vertical wind tunnel. And the idea was that all these cameras would shoot from each angle, and then they would use software after the fact to create, if you like, synthetic camera moves, so that the camera would appear to be moving, and in fact, of course, all the cameras were stationary. And the actors had to do weeks of training to do this indoor skydiving, and they'd been training probably for a couple of weeks before we all arrived with all of our kit. And they had to wear special contact lenses because the wind, normally when you were doing skydiving, you wear goggles, but they couldn't do that. So they had to wear special contact lenses to protect their eyes in the very high wind velocity in the tunnel. And despite all the effort, 3 days of setup and shooting, and I had a stinking cold as well during it, which I distinctly remember. Despite all that effort, the entire sequence lasts no more than a minute in the final film. And they added so much camera shake to the final finished shot that arguably most of the benefits of shooting what were 3.8 gigabytes a second of data, that was probably lost. You probably could have done it on a camera phone and no one would notice. But it was an interesting exercise and an experience. So they did do an updated version of the camera just shortly before they pulled the plug on the whole project, and that was called the Evolution. It was a bit smaller, and that was used for some shots in Tim Burton's 2010 film Alice in Wonderland, and particularly the close-up shots that were done of the Red Queen, played by Helena Bonham Carter, because her head was actually blown up digitally to appear 3 times its normal size in the film. So actually the extra resolution from the 4K camera was very useful to capture extra detail on the face, so that it didn't look, the effects of blowing up that much weren't so significant. So Panavision, one of the major film equipment providers, been around for a very long time. In 2005, they introduced Genesis Camera, and that was made in partnership with Sony, based on the same sensor that Sony used in their F35 camera. And that was a reasonably successful camera. It was used on many films, mostly recording to tape, hard disk, and it also had an optional onboard solid-state recorder, which you can see in the picture there. Now, in 2010, the German film equipment company Arri came onto the scene. Not that Arri are a new company, they've been around for over 100 years, but they came onto the digital camera market with the Alexa camera. And the first model that they produced was a 35mm single sensor camera, and it had a horizontal resolution of 2.8K, so 2,800 pixels across, so more than HD, but not as much as that DOS camera. And it had an uncompressed raw output of 12 bits per pixel, which is actually still a very good dynamic range. And it has a rolling shutter, but that shutter is actually very fast, so it doesn't produce too many of those unpleasant artifacts I was showing you earlier. Now, the quality of the images that the Alexa produced was, without doubt, a revelation to cinematographers. Just a very natural way it reproduced skin tones and textures, it had very low noise, and this very wide dynamic range. And it was the first camera that was widely acknowledged by professionals in the industry to be as good as, or in some cases maybe even better than film under some circumstances. And so as a result, obviously, it became extremely popular. And it spawned a whole series of different models, all based on this same sensor technology, but with upgraded resolutions, and also eventually built-in recording technology, which I will come back to later. So the first feature that was shot entirely in RAW on the Alexa was 2011 film Extremely Loud and Incredibly Close, that starred Tom Hanks and Sandra Bullock. And that was recorded onto a solid-state, external solid-state disc recorder that was made by my company. Another one of the early films was Gravity, and that also starred Sandra Bullock alongside George Clooney this time. And since then, literally many thousands of productions have completed with this camera or one of its updated models. So, how do we compare them? Digital sensors that were used in the very earliest cameras undoubtedly were lacking in either resolution or dynamic range, or both. They could produce reasonable images, and many productions were shot that still stand up today. They don't look terrible. There's a lot of care was needed while shooting them. That was the main thing. You really needed to be careful to avoid underexposure, because then you would be into noise, and you really had to avoid overexposure, because on a digital sensor you tend to get very hard clipping when you overexpose, whereas film has a much softer roll-off when you overexpose it. So I think today most industry professionals would probably agree that digital sensors can now exceed the performance of film, but that's only been true relatively recently. And the fundamental difference in the way that images are captured on film and on digital image sensors makes comparisons inherently subjective at the end of the day. There's only so many properties you can measure using a test chart. The most important property is always just whether the images look pleasing to the eye and to the cinematographer shooting them, and also to the actors and actresses in them. So in a film camera, obviously the storage media was built in inherently because it was the film. But none of these early digital cinema cameras had internal storage in them because it was impractical in the early 2000s to actually integrate enough storage to capture those very high quality uncompressed images. So they ended up either being tethered to external recorders via cables, or later on recorder units appeared that could be mounted on the camera. So let's look at some of the pros and cons then of the various storage media technologies that have been used. Excuse me. So starting with digital videotape, that had the benefits being very, very stable technology. It's relatively low cost, and it was widely deployed in broadcast, widely understood. However, it was always compressed. Certainly, compression was needed to reduce the cassette size to something that was practical to put on the camera. So there were uncompressed tape formats, but they were seriously large washing machine size machines. And of course, when you introduce compression, you get image artifacts, and you don't generally want that. for high quality image capture. So the most common tape system used with digital cinema cameras was the same as HD Camera SR format, which I mentioned earlier. That could record at 880 megabits a second, and that was enough to handle full RGB HD images of the type produced by those early cameras like the Genesis. And the Sony SRW1, which is the recorder you can see in the image, was the compact portable machine that was used on cameras. Although it worked with all those RGB HD type cameras, it doesn't work with raw outputting cameras like the Alexa. Many of you are probably familiar with computer data tapes, of which, of course, there are a dizzying array of different types. Would any of those be suitable? Well, basically, unfortunately. Data tape drives are not designed to sustain constant high data rates. For instance, LTO5, which was tape format introduced in 2010, around the same time as these cameras, excuse me, that has a maximum speed of 140 megabytes a second. But that's very hard to achieve. If the tape drive experiences any kind of problem with the tape, it will slow down to try and reduce the chance of an error. And if it really gets in a mess, it will actually stop the tape, back up, and retry writing the block. And that can take seconds to happen. So obviously that's no good when you have a constant high data rate stream coming in, because immediately you're going to have a buffering error. So videotape machines get around this by using error correction and concealment. So they may still experience errors, but on playback, they'll actually conceal those errors, so you hopefully can't see them. And of course, that means what you record on a videotape machine digitally isn't necessarily exactly what you get back. It'll be an approximation of it, but it isn't exact. So hard disks then were the only practical technology for a long time that could be used for uncompressed storage. Solid state disks did exist, but they were simply just too expensive in the early days. So modern disks, they can sustain a very high data rate as long as you minimize seeks. And they have a pretty low error rate as well. But they're not designed to operate in either extreme temperatures or in high vibration or high G-force environments. So think vehicles, helicopters, that sort of thing. Filming in deserts, filming, in the Arctic and so on. So all of those features they're features of filmmaking, and you need to be able to do those things. And so high vibration G-forces can actually cause the head actuator to move off the correct track of the disk, and that can cause write errors or even corruption in the disk. So one production that I was involved with had a problem when they were trying to shoot guns in an indoor stage. And it turned out that the shock wave from the gunshots were actually causing the hard disk in the recorder to stop recording temporarily because they realised their heads had moved when they shouldn't have done. And that caused the buffer overflow and the recording to stop. And the solution eventually was to actually pad the recorder with a shock absorbing material to try and reduce the effect of the shock wave hitting it. But these are the sorts of problems that you have trying to use hard disks in an environment they weren't really designed for. So also high performance disks are relatively large, and I realise when I say this that compared to the disks that many of you are familiar with, these are still quite small, but we're talking about 3.5 inch, 2.5 inch disks. And they also generate a lot of noise, and they consume a lot of power, which means cooling fans, and generally you don't want too much noise right near your microphone, which if you have hard disk mounted on camera, obviously it's going to place the microphones. So hard disk recorders had to be treated with care, and except in very controlled circumstances, you couldn't really mount them on a camera. They had to be tethered. So solid state disks, brilliant. They solved most of those problems associated with hard disks, but unfortunately they introduced a whole lot of new ones, all of their own. And as soon as the prices fell sufficiently, they very rapidly replaced hard disks in recording applications. So they basically enabled a whole new generation of recorders that could be either mounted on or integrated into a camera. The power consumption with SSDs is still very much an issue, but on the other hand, they can operate at much higher temperatures. So typically, they can operate up to 70 degrees C, which you wouldn't want to put your hard disks through. Modern SSDs are based on NAND flash technology. The flash was first introduced, in fact, as long ago as 1987. And it was the development of the floating gate MOSFET technology that was used originally in EEPROMs. Now, a NAND flash chip is logically divided up into blocks, which typically are a few megabytes in size, and each block consisted of pages, which are generally a few kilobytes. Now, before any data can be written to a block, a whole block must be erased, and that's a relatively slow operation. But once it has been erased, then individual pages can be read and written quite freely. Thank you, Roger. Excuse me while I'm clearing the thread. So all solid-state disks contain a controller, and that's responsible for presenting the host computer it's connected to with what looks like a hard disk. So what that means is an interface that appears to be an array of logical sectors that can be freely read or written in any order. But the inherent properties of flash, which I just discussed then, mean that a complex translation layer is required between those logical addresses and the physical location of the data on the flash itself. So blocks can only actually be erased, programmed and erased a certain number of times, after which they become unreliable. So to maximize the lifetime of the device, a technique called wear leveling is used. What that does is it tries to spread out the program arrays over all the blocks in the device so that you don't have certain blocks that are worn out whilst other blocks have not been used at all. And because individual pages of flash can't be modified without first erasing the whole block they belong to, whenever you want to write new data to an SSD, it has to be placed into new pages that haven't been written before. And inevitably, the original pages get left because the block that they're contained in probably has other useful data still in it. So over time, this leads to a lot of blocks which have only partially useful data in them. And the free space, if you like, on the disk is fragmented between all of those blocks. Eventually, you get to the point where the number of free blocks starts to run low. And at that point, the SSD controller has to run a kind of a garbage collection process, which means going through all of these blocks where there are partially used blocks and collecting up the useful data from them, consolidating them down and writing them into new blocks, thus freeing up hopefully more blocks than you use, and that's the way you get the space back. So flash cells are inherently unreliable, and I like telling people this because a lot of people don't realise how unreliable flash is. It suffers corruption all the time. It only works at all because there's lots of extra error correction in every page. So generally, depending on the level or the technology of flash you're talking about, you need a certain amount of extra space per page, and that's used for these error correction codes, which enable a certain number of bit errors within that page to be corrected. You can think of it a bit like a Hamming code, something like that. The SSD controller has to all the time carefully monitor read error rates on all the pages on the device. And just when it thinks that the data is going to become unreadable soon, it has to copy the data out. And the trick is making sure you do it not too late, but also not too early. Because if you do it too early, again, you affect the lifetime of the device. So that process is actually very complicated and usually very proprietary. It involves a lot of knowledge of the precise flash type, manufacturer, and so on. And it's one of the major difficulties actually producing a reliable device. So a mapping table is needed then to keep track of the physical location in flash of all of these logical sectors, which, as you've gathered from what I've just said, tend to be scattered around the physical flash in a completely arbitrary way. And so efficient implementation and handling of that table is essential to maintaining any kind of high performance. So there's a lot going on in an SSD controller. And the firmware on it is critical to the reliability and the performance characteristics of the product that you end up with. So for recording applications then, there are quite a few considerations which may not be so relevant for consumer use or maybe other types of business use. So for recording, we're concerned about reading and writing large sequential blocks of data, primarily. And SSD benchmarks frequently concentrate on small block performance, small block IOs per second. That's important for databases and general file servers and so on, but for recording, what we're doing is writing huge blocks of image data, and so that isn't so relevant. And of course, this means that often SSDs are optimized for that small block performance. It must be possible to overwrite a whole disk at full performance. Now, the consumer SSD that you might have in your laptop probably contains a cache that enables you to write a certain amount of data very quickly. But once that cache is full, performance suddenly drops off a cliff. And that cache then has to be emptied, which is a much slower process. So for recording, again, that's no good. What we want is sustained high performance. And thermal management is needed as well, because writing to an SSD, the erasing is actually the part that generates most heat. And so when you're writing to an SSD, it generates a lot more power than when you read it from it. So good thermal management is needed to make sure that the disk doesn't actually overheat during very sustained high data rate writing. We don't want performance to drop over time either. A lot of SSDs gradually lose their performance as they use more and more due to the fragmentation that I was talking about earlier. So for recording, the SSD controller's garbage collection must be tuned to work with that kind of application in mind, and also not to get in the way of the recording application by suddenly deciding to garbage collect whilst you're blowing up the bridge or whatever it is, you know. Accurate reporting of data corruption. You may not believe it, but a lot of consumer devices don't bother reporting when corruption has occurred on your disk. They just give you back corrupt data. I suppose the thinking is most people are used to their computers crashing or misbehaving in some way, and they'll never pin it on the SSD, will they? It could be anything. But an error message coming up saying about a block on your SSD would probably lead to the owner taking it back to the shop for possibly a warranty repair. So I think that's probably why they did it. Of course, for recording media, any corruption at all is bad news. And it is, of course, preferable to know about it sooner rather than later, because if you know you don't have the shot, you can reshoot it straight away. If you find out a week later, it might be too late. The really big one is predictable behavior following surprise power loss. Cameras generally battery-powered devices, and recording media is designed, of course, to be easily removed. So power loss without any warning is a frequent occurrence for recording media. And a lot of SSDs don't cope with this at all well. The problems that you can get range from either the drive becoming totally unresponsive, random data corruption anywhere on the media, reduced performance possibly, or even just a lengthy rebuild process when you next power it on, which might take minutes. So we've seen all of those things on different models of SSD. And so at my company, we have spent a huge amount of time over the years working with development partners we have at our SSD vendors to optimize the firmware to suit these very demanding requirements. And it involves a huge amount of testing primarily. Typically, it takes many months to qualify a new model. So with each generation of NAND flash, the performance problems are getting harder and harder to solve. The earliest types of flash devices are now called SLC, the single level cell. And later developments have brought us MLC, the multi-level cell, TLC, the triple level cell, and QLC, which I'm sure you can guess. And they respectively store 2, 3, and 4 bits per cell. So these new devices have all helped to massively reduce the cost per gigabyte of flash storage, but at the expense of a much reduced lifetime and increasingly elaborate error correction being needed as well. So SLC flash typically had a lifetime of, say, 100,000 program erase cycles per block. And that's actually far more than you would need if you assume, say, a 5 to 10 year lifetime for recording media. But on the other hand, some consumer grade QLC flash can be rated as low as only 100 program array cycles, which is maybe just about adequate for consumer use, but it's no use at all for the kind of applications that we're interested in. So recording media generally needs to use what they call industrial or enterprise grades of flash, which have a bit, even in these generations, they have a bit of a higher guaranteed lifetime, but they cost a lot more, of course. So let's go on and have a look now then at some of the other technologies that we need to create practical recorders. RAID, I'm sure many of you are probably familiar with that term. Redundant array of inexpensive disks, which I always think is a bit of a misnomer because many RAID applications actually there's no redundancy and usually the disks are extremely expensive. So in both hard disk and SSD based recorders, it's usually the case that an individual disk will not be fast enough, so multiple disks have to be arranged in parallel and data striped across them in some way. The most basic level is RAID 0, and that is the level where there is no redundancy. In other words, any disk fails and you've lost the lot. Other common levels that are used are RAID 1, which essentially mirrors all of your data. Every disk has an identical copy. And RAID 5, where there is a parity copy stored of your data. So one disk, well, actually parity is distributed over all disks, but effectively one disk is dedicated to parity. And that enables you to recover from the failure of any individual disk in the array. Now, all of those configurations have been used on recorders over the years. Nowadays, RAID 0 is actually the most common. And that's because SSDs are now sufficiently reliable that failure is very rare. And they're also, on the other hand, still sufficiently expensive that customers don't want to sacrifice the storage capacity that you would have to use any of these RAID layers to guard against the possibility of failure. So it's really mainly an economic decision. It's led to that. Store any data on disks, you need a file system of some sort. Until quite recently, the most common method of working with uncompressed digital cinema images was to store each frame in a separate file, and each shot would be stored in its own directory. And the frames themselves range in size from, say, a few megabytes up to tens of megabytes, depending on camera. A typical storage media may be 60 minutes, 24 frames per second, so you can say of the order of 100,000 files or frames stored on the media. So the job of the file system then is to record where each of those files are, as well as all the file names, permissions, access times, and so on. So all the information that isn't actual file data content is called metadata. The common file systems are not that good at maintaining high and predictable performance while you're creating lots of new files on them. And that's because that generates lots of file system metadata, which also has to be organized and written onto the media. Another issue you get is if you're using a file system on top of a RAID array, particularly ones that involve parity, because most file systems are not aware that they're sat on such an array. And file systems generally will divide the idea of the logical space they have available into allocation units. But when those allocation units don't align with the underlying stripes on the RAID array, that can lead to reduced performance. So I decided to take a different approach when I was designing the file system we use at my company, and design it specifically for the job, because, why not? So let's look at the main characteristics of the codec file system. So firstly, the RAID management layer is actually integrated directly into the file system. And we use variable stripe sizes to suit the different recording formats. That means you can mix different recordings from different types of camera or different media, for instance, picture and sound, on the same array, and have the stripe sizes organized to allow everything to be nicely aligned, but also not to waste too much space. The second point about it is it isn't really a file system, but there are no files as such. I would more accurately call it an object store. And that it consists of a simple database, holds objects representing shots and so on, an allocation table describing where everything is stored, and the file system metadata, which in this case is this object database, that's written onto the media at regular intervals in a very predictable way, and that means we can control the impact that has on performance, and it means we can maintain a guaranteed recording rate. And we also optimize the encoding of these objects that we store to minimize their size for the most common cases that occur. So with all those design features, it means that we were able to create a file system that allowed us to almost fully utilize the performance of the underlying storage. Now, film production workflow, it's a very involved topic, and I'm not going to go into it today in great depth because we'll be here for another couple of hours. So suffice to say that different departments require access to the recorded material in various forms. For instance, editorial departments might require scaled down, compressed versions of each shot, say as a QuickTime file perhaps. On the other hand, visual effects artists, they typically need only short sequences of material, but they need them full resolution, uncompressed, and they generally have their own file formats that they prefer as well. So in the early days, it was like the Wild West in digital production. Every single production was like a science project. They set their own standards, file formats, naming, and so on, which they insisted upon. And that created obviously a problem for the crew who were charged with delivering the files to these various departments. So to help solve that, I came up with the idea of using what we call a virtual file system. So simply put, you configure your system up front with the types of files that you know you're going to require and the way that they should be named. So that's using various metadata captured during the shoot, like say timecode or the shot name or the tape or whatever it is. When the recording media is actually loaded onto the system, all the rules get applied and a whole set of virtual files are instantly created that correspond to the media, the material that's been shot. But the actual contents of each file is only actually calculated when you try to read it. So the files appear instantly, but then they're made on the fly. And that made the system very flexible and able to meet the exact requirements of all these different productions and studios without having to do a lot of time-consuming conversions and renaming operations after capture. So the first hard disk recorders on the market were relatively large, to be fair. They were based on standard PC technology. So typically Sterling class motherboard, a couple of Intel Xeon processors, loads of RAM, SCSI for attaching an array of hard disks, and a PCI Express video interface board of some sort for the camera. So as you can imagine, with all that hardware, none of these could be considered portable. You can see there in the pictures actually the prototype for the first recording device that we produced. It's two 19-inch racks, 8U. So it was reasonably large. It lived in a shock-absorbing flight case on wheels that was wheeled about, so it could be moved, but it clearly wasn't something you're going to lug about too much. So the next stage of developments saw recorders shrink quite dramatically in size to the point that mounting actually on a camera was feasible. And that was really enabled by the solid-state disks that I talked about. Initially, those came in a 2.5-inch form factor, which was similar to laptop hard drives at the time. In fact, that's really what the form factor was made for. And eventually, even smaller versions in 1.8-inch were available before it moved to what's called the M.2 standard. You might have seen these things if you've bought a modern PC recently. They're very common about system disks. So that's the storage dealt with, but the next challenge then was to reduce the size of the electronics to make a much more compact and lower power product overall. And the key technology that enabled us to do this was the field programmable gate array, or FPGA. Now, if you're not familiar with FPGAs, you can think of them as programmable logic in a chip. Depending on the model, they consist of between thousands and millions, or even nowadays tens of millions, of configurable logic blocks, or CLDs for short. They have many hundreds of I/O pins and a flexible interconnect within them that allows everything to be hooked up. They also contain distributed static RAM, and that stores effectively defines the function of all the lookup tables of all of these CLBs. So this lookup table is essentially it's a logic function that decides what the output will be for any combination of the inputs. And the static RAM also configures the interconnect within the device too. So modern FPGAs can handle logic running at clock rates of a few hundred megahertz, so up to 300, 400, 500 megahertz is possible. And for anything beyond that, they have dedicated high-speed serial interfaces, and those run into the gigahertz or tens of gigahertz range. And they are used to handle things like high-speed video interfaces or PCI Express, all of which are serial protocols that run in the gigahertz range. But because the actual logic clock rate is relatively low, so if you compare it to your modern Intel processor, which is running at gigahertz for logic, FPGAs are relatively slow compared to those kind of devices. So the key to getting a lot of work done in FPGA is actually to parallelize it as much as you possibly can. So it would be far too complicated to actually program one of these devices by hand. So all the major vendors who make them provide very sophisticated tool sets to make the job a lot easier. So you describe your logic using a high-level language, typically that's either Verilog or VHDL. And that's then compiled and mapped onto the logic blocks in the device, and that process is called placement. And the final part of the process is routing, which sets up all the interconnections between those logic cells. Now the routing process has to ensure that all your setup and hold times are maintained for the input of every flip-flop in the design. Bearing in mind there could be tens of millions of these flip-flops. And that process, even running on modern machines, takes hours and hours and hours to complete for a large complex design. And it might not succeed at all. And if the tools can't meet timing requirements for your design, we then have to go in, try and find out what they don't like, and perhaps try and help them out a bit by adding extra register stages here and there. And that process is called achieving timing closure. And that actually can be a fairly significant fraction of the design time compared to writing the logic itself. So FPGAs can handle all the interfaces that we need for a typical disk recorder. HDSDI is a video interface, runs at 1.5, 3 or 6 gigahertz. SATA, another serial interface, PCI Express, disk. SD-RAM for the buffer memory. Again, they have specialized interfaces and blocks to handle all of these things. And you can also now get FPGA devices that contain embedded CPUs, typically nowadays ARM cores. And that eliminates another chip, another separate chip that you need from the design. So you pretty much can have a single chip design these days. So let's then have a look at some actual recorders. I'm going to concentrate on the products which I'm most familiar with, which are the ones that were aimed at the high end of the market. So big budget film and TV drama productions. Inevitably, that means my own company's products are going to feature here, but I have included a few others that were around at the time for context as well. And of course, there are lots of other excellent products out there on the market and different segments of the market, but usually they operate at lower data rates and they utilize various different forms of compression. So this is one of the first hard disk recording systems, the Director's Friend. We had a slightly less friendly nickname for it, which I won't disclose. And that was designed allegedly specifically for use on a film set. It was used mainly, most notably anyway, to record the film Russian Ark, which was shot on a Sony F900 camera, and it was shot as a continuous 96-minute take with no cuts. And of course, that's impossible to do on film because you can't, any film camera will take that much film. But it wasn't a very practical system.
It's back, sorry. Might come out of Zoom, go back in again.
I think somebody needs to mute. So it wasn't a very practical system. The main unit that you can see on the left and the hard disks, which the person in the middle photo is carrying, were connected together with standard SCSI cables with their very fragile connectors. And seeing as you would need to be undoing those multiple times per day, that clearly wasn't going to be practical. And actually seeing this was one of the main things that spurred me on to developing something better. So S2 were one of the major competitors my company had in the early days. Their digital field recorder was introduced in 2003. That was just after I started development on products that I was working on. Recorded to a removable magazine called a DMAG, and they held between either 18 or 36 minutes of video. It was used a lot with the Thomson Viper film stream camera at the time. That was the most popular camera, and a number of films were recorded on it, including Zodiac, which we talked about earlier. So this was the first product that was released from my company in 2005. Worked with all those HD cameras I talked about, as well as the 4K Dulce Origin camera. But the two removable disc packs were normally used independently, but for the Origin, that had a much higher data rate, around 400 megabytes a second, and they had to be used in parallel in order to capture that data. And the first major production to shoot entirely using this system was the 2008 film Speed Racer, which was shot on Sony F900s cameras. So a couple of years later, we came out with a portable, considerably smaller, designed to be worn over the shoulder by an operator. I don't know if you can actually see what it says on the advertising poster there, possibly not. Just don't read it. It says it was about the size of a toaster and possibly the best thing since sliced bread. I'm not sure that's strictly true. I didn't write it in my defense. So it recorded onto smaller disc packs, and they featured essentially laptop hard drives, and we mounted them internally on this complicated rubber damper arrangement to try and minimise the effect of shocking vibration on discs. And because they were much smaller disc packs, they were slower than the original recorder. So we also added Jpeg 2000 compression, which was used to reduce the data rate by about a factor of 3. So another product from S2, the OV1, that was introduced in 2009 and was a camera-mounted product, as you can see, recording onto a solid-state drive called a flash Mac. That came out roughly the same time as our codex onboard M, which we launched in the beginning of 2010. That one again had the option to use Jpeg 2000, but it could also, thanks to its faster flash drives, record uncompressed. And particularly, it could record raw data from this Arri Alexa camera, which I mentioned earlier, which also was introduced in 2010. And we worked very closely with Arri to ensure that this recorder and their camera work together seamlessly and that the workflow was as simple as possible. As a result of that, this was the first recorder that was certified for use with the Alexa, and was subsequently used to shoot by almost every production that used the Alexa for raw. It was also used in its Jpeg 2000 mode on a number of television programs, including a few seasons of HBO's Game of Thrones. And you can see on the bottom right there just how small the recording media was, the one on the left there from the onboard, compared to the portable in the middle, and on the right the original codex recorder. And this is in a space of 5 years. So the onboard S, another couple of years later, that was just a repackaging really of the onboard M, but the main thing was it included this new capture drive, which used 1.8-inch SSDs, which were the new thing at that time. And it was capable of about 400 megabytes a second. It's about the size of a cigarette packet, that drive, the scale. And that's faster than one of those original codex recorder drives. So, although it was used a lot with the Alexa, it was also designed to work with other cameras, so for instance, the Canon C500. And in 2015, the C500 and the codex on board was flown on the International Space Station to shoot an IMAX documentary. You can see there in the picture, it's installed in the ISS's Kepler observation module. And before it could go up, NASA had to do a whole load of tests, and that's mainly to make sure it won't interfere with anything on the space station, and also to test whether it will survive in space, essentially, so in a high radiation environment. And the way they do that is they just batter the equipment with more and more radiation until it stops working. So after they'd done this, I asked the NASA engineer how it had done, and he said, well, The amount of radiation they'd used was enough to kill all of the crew on the space station several times over. So I said, does that mean it's okay to fly? Agreed that it probably was all right. So if this works, which hopefully it will, I apologise if you can't hear it. This is after they completed those tests and somebody at NASA weighed in the Geiger counter over the recorder. And they didn't let us have it back until that had calmed down a bit. So the next logical step towards a more convenient system was to incorporate the recording function directly within the camera body itself. During the NAB 2012 trade show in Las Vegas, I got talking to one of the senior ARRI engineers over dinner about the possibility of incorporating our technology directly within the camera. At that time, the Alexa was able to record compressed ProRes format, which is a format that's used in television quite widely, onto an internal memory stick. But if you wanted to record that high quality raw data, you still needed an external recorder. But I realised that it was possible to port our recording engine onto the existing hardware within the Alexa that was used for this ProRes compression. And in fact, all that would be needed would be to add a new storage media to the camera. And so by the end of the evening, we'd actually designed the system on the back of a napkin pretty much. And once we got management agreement for it all, development started. And that new capture drive that we introduced became known as an XR drive, 512 gigabytes, and capable of 800 megabytes a second, which is actually twice the data rate that the previous year's drive had been capable of. So you can see that really at this time, flash technology was really improving really dramatically. And that was all launched in 2013 with back-end workflow systems provided by my company. And we continued the partnership with ARRI to create a recording system for their Alexa 65 camera. And that was a 65mm version of the successful Alexa sensor that they created by stitching 3 of the Alexa sensors together on the same die. And that had a resolution of over 6,500 pixels. So that dramatically increased bandwidth, required another new storage media, as you would imagine, and another new capture drive format was born, called the SXR. That one was based on these M2 PCI Express modules, 2 terabytes and capable of 2,500 megabytes a second, which is over 3 times the XR drive from the previous year. So, this really is quite a dramatic escalation in what's possible over these years. So during the development of the Alexa 65 and that new recording media, ARRI were approached by the producer of Spectre, which was at the time the next James Bond film, with a request to use a prototype camera for what they described as test shots. It turned out to be the scene where Bond is on a speedboat on the Thames at dusk. He's being chased and shot at by a helicopter, which eventually blows up, as I recall. And the picture you can see there was actually taken, it's not from the film, it was actually taken during the shoot. So as it was described as a test, we weren't too concerned about giving out one of our R&D drives for them to use. But unfortunately, being a development unit, there were still a few issues to iron out. And it turned out, unfortunately, this particular drive turned out not to like too much heat. And when we tried to route the data back, we ended up with errors. We eventually realised what the problem was, and we solved it by putting it in the fridge and then reading the data small seconds at a time until we got it all back. And luckily we did retrieve it all, and some of it actually made it to the final cut as well. And in fact, if you watch this film on a big screen, it's quite obvious which shots are from this Alexa 65, because all the film grain suddenly disappears. It's really noticeable. And it's a very, very good illustration of how much better than film digital cameras have become at this point, especially in low light situations. So just to bring us up to date, this is the latest generation recording drive. It's used by ARRI's Alexa Mini LF camera, which, as you can see, possibly from the size of the lens, is a much smaller camera than the previous models. And although the compact drive itself, you might think, looks very similar to that SXR drive, it's only about a third the size, in fact. It still has a capacity of 1 terabyte and records up to about 1,000 megabytes a second. I said earlier I wasn't going to dwell too much on workflow, and I won't, but just to complete this, a couple of the back-end systems we produced. On the left, the digital lab, that was used with some of the original recorders, the portable, and the vault on the right. I don't worry if you can't read the text. It's a modular system designed to go on set, work with the onboard recorders, the Alexa cameras, as well as other recording media produced by Canon, Red, and Sony. And just a couple of examples then of Thunderbolt and USB connected docks that we make. These are used generally on Macs in the Thunderbolt interface. And those two are for the SXR and compact drives. So finally, let's have a look at some of the terrible, terrible things customers do to the equipment. This unfortunate onboard M recorder was run over by a car. But despite that, and fairly extensive damage, it's still actually powered up and worked when we tried it in the lab. As you can see, the display's still on. And I'd love to be able to say that this was a one-off kind of occurrence, but there are many similar stories. I know of a camera and recorder that was hit by a bus. I was asked to do data recovery on that particular incident. And a camera and an onboard recorder that were mounted on a camera crane on a vehicle, doing some stunt driving, which went a bit wrong and hit a telegraph pole. The recording drive from a telegraph pole incident was actually found in a nearby bush and still worked. And it was actually quite funny to watch the material that it recorded, because you could see this pole approaching after the last few seconds until it all went black. I doubt the insurance company saw the funny side, because it completely wrote off the very expensive camera and the crane as well. And it caused the production quite some trouble getting a replacement crane, actually. I probably should have thanked the production. So these are just a few recent productions that are using our technology, lots and lots now, mostly recording media technology. So yeah, although the history I've covered this afternoon is extremely recent by CCS standards, I hope that you found it interesting anyway. Thank you very much.
Delwyn, a truly fascinating exploration of the way in which the technology has evolved, and the way that it's got so much tinier and at the same time faster. It is an extraordinary tale. There are various questions that people have got, if I can. I wonder.
Put it on share.
Ah, yes. Okay, right. Oh, good. We've now got pictures of Delwyn. That's nice. Right. I've got there's a question Terry Broggett has asked whether all of the equipment is designed to be used by right-handed people.
Yeah, that's an interesting one. Some of our recorders have actually had removable control panels, which enable them to be mounted on the right or the left. Cameras generally are designed, certainly the ones in this market, are designed. Actually, I'm just realised that the microphone. Can you hear me? Sorry about that. Yeah, some of our recorders have both have removable control panels that can be mounted on either side. But yeah, a lot of the cameras are fixed essentially, so that a lot of them are actually arranged more for the operator and for the assistant to operate them. So they generally have on the right-hand side the controls that the assistant would need, and on the left-hand side the controls that the operator would need.
Okay, thank you.
There's a question from Vince Chadwick, if you'd like to ask the question.
Yeah, can you hear me?
Yes.
Yeah.
Okay, yeah, it's not about cameras per se, but I wonder if you can answer it anyway. In what format and in what media are so-called films delivered to a cinema these days, or is it done on some sort of online system?
Yeah, there is a yes, there are digital encrypted standards that are used for delivery to cinemas nowadays. Yeah.
And is that sent on some device like a solid state disk, or would it be downloaded?
Well, I couldn't tell you what happens now. I know for some time hard disks would be delivered. I would imagine nowadays, I'm not really that involved in the presentation side of things, so I'm speaking a little outside my knowledge, but I think probably now they would be downloaded.
Okay, thanks very much.
Next, from Troy Kane Astati, apologies for pronunciation. Would you like to ask your question?
Hello, can you hear me okay?
Yes, fine.
Yes.
Hello, do you hear me all right?
Yes, we can hear you fine.
So I know that certain stills cameras these days, some stills cameras these days use larger format sensors like medium 4/3 or even bigger. Do video cameras also have larger sensors, or is it still primarily 35mm? And if so, why?
Well, mainly it's because of the lenses. So there's a very large installed base, if you like, of 35mm format cinema lenses out there. Lenses are very expensive. So changing the sensor format does carry a sort of penalty, if you like. That said, there are larger format sensors out there. So I mentioned the Alexa 65, which works with 65mm film lenses, as well as a similar format that Harry came up with themselves. And there are also there's an intermediate large format size, which I can't quite quote you the exact dimensions of, but there are a number of cameras from Harry and from Red that have those intermediate size sensors. Yes.
Okay, thank you.
There's a question here from David Hunt asking about the how big the market is for cinema cameras and recorders, number of units. I was also intrigued in general terms that the sort of cost of the various boxes you were showing us, just in orders of magnitude.
That's what I was leading up to as well, thinking that any individual unit you would perhaps sell in relatively small quantities, and inevitably it has to be very expensive.
Yeah, I mean, there's a big range. So at the top end of the market, certainly at the time, say in the early 2000s, a lot of those cameras that I showed you were all in the sort of several $100,000 kind of price bracket. And yeah, our equipment would be in similar price bracket. And yes, it was a small market, but as time has gone on, there are so many more cameras on the market now. There's a whole range of different price points, so you can get really quite good moving picture cameras now. Companies like Blackmagic produce a lot of lower end and cheaper cameras that cost the order of, a few $1,000s. But again, those cameras have compromises of various sorts, so generally compression, maybe the sensors aren't quite so good. But yeah, at the top end prices have come down a lot, but you're still looking at probably tens of thousands of dollars for a decent camera these days.
There's a question from Brian Spall in the room.
Yes, Delwyn, a couple of quick questions. How do the latest digital cameras compare with 65mm? And you say the early digital cameras were heavy and bulky, but how did that compare to a 35mm camera with a 2,000-foot magazine on the top and 2,000 foot of film if you never picked it up? Quite heavy.
Yeah, no, it's a very good question. So for the 65mm question, obviously 65mm film is at least 4 times the area. So 65mm film you wouldn't want to compare to 35mm camera types. But yeah, when it comes to the Alexa 65, for instance, I think that those properties scale up, if you like. So you've got a sensor that is equally 4 times as large as well, 3 times as large. So I think that it does stack up very well still against 65mm film. Yes. Sorry, what was the other question?
You say the cameras were bulky.
Oh,
the
right,
cameras
yes.
were bulky, but you know,
Yes.
thinking of a film camera with a
Yeah.
35mm magazine or even 65mm, which is
Yeah.
roughly 4 times the weight.
But of course, for handheld, you did have much smaller magazines,
Yes.
and that's how they did handheld. So you wouldn't put that 2,000 foot mag on a camera that you were going to put on your shoulder. So yes, but agreed with a large mag, and yes, it's comparable. Yeah. Not to say that people didn't want something more convenient, of course.
Oh no, I've used a 16mm reflex, and that needed a tripod, and it certainly couldn't be conveniently handheld.
Yeah. Yeah, it's worth saying as well. I mean, you know, people want all these onboard devices, but then they connect 100 cables to the camera to monitors and goodness knows what on set. So you think, well, why are we bothering? It's because people want what they want, and so you have to provide it. But it also, of course, you don't have to play those cables, and you can go and run a gun sheet.
So the fact that it's got cables means it lightens the camera, because some of the heavyweight stuff can be kept.
Yes,
Camera.
yeah, that's right.
Here's a final question from Alan Taylor. Sure, is Alan there? What provides the best video quality when recorded? RAW, RGB, YC?
VCR.
Yes, what you just put YC.
Well, it depends on the camera. So generally, RGB will be better, almost always. But it depends the quality of RGB. If it's an RGB outputting camera, then the quality depends on whether it's a 3 sensor or a single sensor. The single sensor cameras have to do that reconstruction process that I mentioned, the layering. The complexity of the algorithm you can build into a camera is not as great as one that you can run on the software after the fact. So that means the cameras that single sensor cameras are outputting a reconstructed image are going to have some compromise on the quality of that image, and you're better off recording the raw data from them, which is also less dense than the RGB, and then doing the reconstruction after the fact. YC VCR is not really used in digital filmmaking. It's really a television thing, and really the thing that distinguished those early cameras that were aimed at digital cinematography rather than television was the fact that they could output RGB and not YC VCR. So that's lumens and the 2 chromiums that I mentioned.
Well, thank you for that. Before I ask Doran Swade, our chairman, to just propose a vote of thanks to you, can I announce that our next meeting is Brian Shearing, who will be talking, giving the second part of his talk about Genesis. And also, if you go to the CCS website, you will see details of an event being held at Paderborn in Germany by the Heinz Nixdorf Museum there, who are receiving an award from the IEEE as a commemoration of the work of the museum. And that will be webcast, and details of that are on our website, and they're good friends of ours, and we're delighted at their success. We wish them well for the future. It may be, if the situation continues to improve, it may be time to have another visit there, but we wish them well. If you'd like to see that ceremony and that event, go to our website and you can pick up the link. And now over to Doran. Doran, would you like to just say a final closing word of thanks to Delwyn?
Thank you, Roger. Delwyn, that was just absolutely fascinating. I mean, it wasn't just a survey of the technology and the factors involved, but it was also a tutorial, I found, which was hugely valuable. There were elementary things that one might assume we might know, and I think most of us don't. Certainly I didn't. So I think that that combination of both a survey and a tutorial was absolutely invaluable. The thing that I admire hugely about not only the content, but the delivery was the absolutely enviable clarity with which you articulated and structured what you were saying. And that is a great gift, and I was hugely appreciative of that. I think the topic is inherently fascinating. It's also low volume, very highly specialized products, which are something of a sort of black hole for many of us, that, you know, the technology and the principles of technology may be familiar to us, but the actual applications in something like in TV and image processing and visual effects is something that is inherently fascinating and something that is opaque and not accessible to a lot of us. So there are a number of dimensions as to why your talk was so valuable, fascinating, and just to thank you hugely for, I mean, the fact that our attention was gripped throughout, and the quality of the questions that arose, I think, is testimony to the extent to which what you said was greatly appreciated. So huge thanks from all of us.
Thank you, Delwyn.
Look forward to seeing you all at the next meeting. We will look at the sound issues. We have had some problems this afternoon, and we're still learning and feeling our way. And if all was not entirely clear, our apologies, and we'll run another check before next time. It clearly was okay for some and not for others, but we'll look at that and continue to learn lessons. Thank you very much indeed. Bye-bye.
Can I make some more remarks about